Module 1: Waste Management, Principles, Technologies, and Strategies. 1. General background, waste, MFA, and economics. When we talk about waste management, we are dealing with one of the most essential but often overlooked aspects of modern society. Every household, business, factory, and even farm produces waste. Managing it effectively is crucial for public health, environmental protection, and economic efficiency. What is waste? Waste can be defined as any material that is discarded after primary use or that is no longer useful in its current form. It might be solid, liquid, or gaseous, but in this course, we'll focus mostly on solid waste. Material flow analysis, MFA. Material flow analysis is a method for assessing the flow of materials within a system, from input to processing, use, and finally disposal. In waste management, MFA helps us track where resources go, how they are used, and where they end up as waste. Economics of waste management. Waste is not just an environmental issue, it's an economic one. Collection and disposal costs are significant for municipalities. Poor waste management can damage ecosystems, reduce tourism, and increase healthcare costs. On the flip side, recycling and reuse can create jobs, generate income, and save raw materials. 2. Sources, quantities, and composition of waste. The characteristics of waste depend on where it comes from and how it's produced. Sources of waste. Household waste, food scraps, packaging, clothing, broken furniture. Commercial waste, office paper, packaging, electronics. Industrial waste, manufacturing scraps, process residues. Agricultural waste, crop residues, animal manure. Construction and demolition waste, concrete, bricks, wood, metals. Medical waste, sharps, contaminated materials. Quantities of waste. Waste generation varies with economic development, population density, and lifestyle. High-income countries tend to produce more waste per person, often with a higher proportion of packaging and disposable items. Composition of waste. Typical municipal waste might contain organic material, food, yard waste, paper and cardboard, plastics, glass, metals, textiles, hazardous components, batteries, paints. Understanding composition is essential for selecting the right treatment and disposal methods. 3. Legislation, regulation, and control. Waste management is guided by laws and policies that set standards for collection, treatment, and disposal. Key principles in legislation. Polluter pays principle. Those who generate waste must bear the cost of managing it. Waste hierarchy, prioritize prevention, then reuse, recycling, recovery, and finally disposal. Extended producer responsibility, EPR, manufacturers take responsibility for the disposal of products they make. Regulations often address licensing of waste transport and treatment facilities. Standards for landfill design and operation. Restrictions on hazardous waste disposal. 4. Anaerobic digestion. Anaerobic digestion, AD, is a biological process where microorganisms break down organic material in the absence of oxygen. Stages of anaerobic digestion. Hydrolysis, complex organic matter is broken down into simpler molecules. Acidogenesis, these molecules are converted into volatile fatty acids. Acetogenesis, acids are transformed into acetic acid, hydrogen, and carbon dioxide. Methanogenesis, methane-producing bacteria convert acetic acid into methane gas. Benefits of AD. Produces biogas for energy. Reduces waste volume. Generates nutrient-rich digestate for soil amendment. 5. Anaerobic digestion of municipal solid waste, MSW. When applied to MSW, anaerobic digestion focuses on the organic fraction, food waste, garden waste, and paper. Advantages. Energy recovery through biogas. Reduction of greenhouse gas emissions compared to landfill. Challenges. Requires careful separation of non-organic waste before processing. High initial investment in AD facilities. 6. Composting. Composting is the aerobic decomposition of organic matter by microorganisms under controlled conditions. Types of composting. Windrow composting, organic waste is piled into long rows and periodically turned. In-vessel composting, enclosed containers allow better control of temperature and moisture. Vermicomposting uses worms to process organic waste into high-quality compost. Benefits: produces nutrient-rich soil amendments, reduces landfill waste, improves soil structure and fertility. 7. Incineration. Incineration is the combustion of waste at high temperatures to reduce volume and destroy pathogens. Advantages: significant reduction in waste volume, energy recovery from heat. Disadvantages: air pollution if emissions are not properly controlled, high operational cost. 8. Reuse and recycling. Reuse, using an item again in its original form, e.g., refilling glass bottles. Recycling, converting waste materials into new products, e.g., melting down aluminum cans. Advantages: conserves raw materials, reduces energy use in manufacturing, creates jobs in the recycling sector. 9. Recycling technologies. Mechanical recycling, shredding and remolding plastics. Chemical recycling, breaking down plastics into monomers for remanufacture. Paper pulping, reprocessing waste paper into new sheets. Glass remelting, melting and reforming glass products. 10. Waste management behavior, people. Behavioral factors influence waste management success. Education and awareness campaigns can improve participation in recycling and waste separation. Incentives, such as depository fund schemes, also encourage positive behavior. 11. Industrial solid waste, audits and minimization. Waste audits. A systematic review of waste generation in a facility to identify reduction opportunities. Waste minimization. Process modification. Raw material substitution. Improved process control. 12. Waste composition and stabilization behavior. Over time, waste in landfills undergoes chemical and biological changes. Stabilization reduces its environmental impact but can take decades. 13. Landfill site design and management. Modern landfills are engineered systems with liners to prevent leachate escape, leachate collection systems, gas collection systems for methane, daily cover to reduce odors and pests. 14. Risk assessment of landfills. Risk assessment evaluates potential hazards from landfill operations, including gas migration, leachate leakage, and slope stability issues. 15. Pollution from landfills. Major pollution pathways include leachate contamination of groundwater, methane emissions contributing to climate change, odors and airborne particles affecting local residents. 16. Leachate fate, attenuation, and treatment. Leachate is liquid that drains from waste, containing dissolved or suspended contaminants. Treatment may involve biological processes, chemical precipitation, membrane filtration. 17. Industrial waste strategies. Strategies include source reduction, process optimization, waste exchange programs between industries. 18. Municipal solid waste strategies. Integrated waste management systems combining collection, recycling, and disposal. Public-private partnerships to improve service delivery. 19. Decision support systems, DSS, for MSW. DSS use data analysis and modeling to guide waste management decisions, for example, optimizing collection routes or selecting appropriate treatment technologies. 20. Solid waste issues in emerging and developing countries. Challenges include limited financial resources for waste infrastructure, informal recycling sectors, open dumping without environmental controls. We've covered the full scope of waste management, from definitions and sources to advanced technologies, landfill design, and policy strategies.